Thanks for joining, everybody, to the eighth and final night of Introduction to Data Science with Lambda School. We hope you've enjoyed all this, and we hope you've learned something, and we hope that you've learned that there's an awful lot to learn in this area. There really is. There is a lot more where this came from, and we really hope that you come and join us to get, well, still not all of it. You could study this your whole life, but to get a really useful, powerful chunk of it under your belt, so then you can go on and hit the job market and succeed in this exciting area that really is growing, right? This is a cool place to be right now. But I will not wax philosophical. I will pass things on to Ryan for our last lecture.
Hey, everybody. And again, just feel so privileged and honored that you would take time on a Friday evening to be with us. And I'm excited that you're here because we're going to cover some more machine learning and other lessons. So let's get to it. I'll share my screen. And again, this is machine learning from the point of view of really applied machine learning skills, the sort of things that a prospective employer may be looking for in their data scientists. So yesterday we covered regression models, type of model that outputs continuous values, typically floating point numbers. Today we are going to focus on classification. And this is a type of machine learning model, as the glossary definition says, for distinguishing between two or more discrete classes. And I'll give you some examples of what that means in just a moment. But both of these are types of supervised machine learning. So really the idea that you have, in this analogy, a student learning a subject by studying sets of questions and the corresponding answers. You have that answer key, so you learn that mapping from question to answer, and then you can hopefully generalize to some new questions you haven't seen before, but they're on the same topic. For an example of this, here's a diagram from the Harvard Business Review. So this is something that your prospective boss's boss might be reading articles like this in the Harvard Business Review, explaining what is this machine learning thing from a business executive perspective? What can machine learning do? And specifically, here are some examples for supervised learning. You take some sort of an input, like a loan application, and then you predict a response. Will they repay the loan? 0 or 1, no or yes. Or given an advertisement and some user information, will the user click on an ad? 0 or 1, true or false, yes or no. So these are real world type of business examples of classification, a type of supervised learning. And this really is the type of machine learning, supervised learning, that is most common in the business world. And as you can see, even in these examples from this diagram, there are ethical implications in all of this. So if you were to join us as a student in Lambda School, we would discuss both the ethical considerations of these use cases as well as the technical considerations, and always with an eye towards what is practical and applied and what is going to help you get a job. That diagram, by the way, comes from Andrew Ng, who is a Stanford professor of computer science and also the founder of Coursera. So if you've ever taken an online class from Coursera, or you've heard of that platform, well, Andrew's course on machine learning, of all things, was the predecessor to him founding that platform. So truly an expert, even though he's writing in a popularized way for business executives. So in that article, he says, absolutely, supervised learning is by far the most common business application. So that's why we're diving into it tonight. But first, in this distinction between these types of supervised learning, regression or classification, let's take a look at some data here and actually, sorry, I need to open this in playground mode and clear my outputs. And we will run this cell by cell and take a look at some data, just some generated fake data that would be a good fit for classification. So we have here, this is sort of a funny looking scatter plot, right? Because they're not scattered all over the plot. Instead, we have on the y-axis some dots that are at 0.0, and then we have some dots that are up here at 1, and those are the only two possibilities. It's discrete, so it's classification, and there's only the two possibilities, 0 or 1, so it's binary classification. Even though this data set is just artificially generated, you could imagine perhaps on the y-axis, this is whether or not an email is spam, and then the feature here is maybe the mentions of certain pharmaceutical products or sales pitch type of language. Or you could say, what if the target here is maybe whether or not an auto insurance claim is fraudulent, and the feature here is how long ago did they sign up for insurance, a long-time customer or brand new customer. Maybe it's, are they connected with known fraud rings like shady attorneys like Saul Goodman from Better Call Saul, etc. You could imagine whatever example you want to fit in here. But regardless of the example, when you have a classification problem, if you were to scatter plot your data, it would maybe be a funny looking scatter plot like this. We could try to apply a linear regression to this data. Let's see what happens if we do. This is the same exact same sort of code that we used last night. I'll run the cell, and then we'll go through it line by line. So here's what happens if I try to fit a straight line to this data. So there's some good things and some not so good things here. The good thing is that the linear regression has found this general trend that as this feature increases, as we move to the right, then there is a positive association with whether we're predicting a 0 or a 1. So as this feature increases, we're more likely to predict that the email is spam, or that the auto insurance claim is fraudulent, or what have you. And so that's correct. We see that visually in the data. It's good that our line fits that. But one funny thing here is that even though our data is always a 0 or a 1, we're predicting all sorts of values that go beyond those ranges. So we're predicting values that are greater than 1 if we extend to the right side here, and also predicting negative values, which doesn't make any sense if we go farther to the left here. So this is why linear regression, even though in a certain sense it could work, even for classification data, it's not the best choice of model type to fit data like this. So instead, we have another type of model. But before I get into that, let me just make sure everything is clear in this code cell. Okay, so we fit the linear regression model. Then we generated predictions across this entire range of input. We plotted it. That's the same as last night. Let me see if there's any questions. In Slack, I see some questions about ethical considerations. I have some links to reading I really like about that, and I'll post after the lesson. But looks like no questions here on the code example, so I'll keep moving. So this next type of model for classification, it maybe has a confusing name, but it's called logistic regression. But yet logistic regression is not for regression problems. It's for classification problems. So it's a little bit of a misnomer. But it's named that. It still is in a related family of models to the linear regression. And we won't get into the technical details since we're really keeping it applied and practical. But just something to be aware of, that when you're talking about logistic regression, that is a model for classification. One, in fact, of the most common kind of models for classification. And so now here, this code cell is exactly the same, except for that we're using the logistic regression model, but fitting it on the same data, making those predictions. And now the the output, the predictions of that model have been squished. They've been to always stay in a 0 or 1. In fact, in this representation of the model, the predictions are always exactly 0 or 1. So we have here on the left side predicting 0, and then when you cross a certain point, then we say, okay, then now we're going to predict 1 for this data. But that is if we use the predict method for the logistic regression implementation in scikit-learn in Python, it's going to give us a 0 or 1, but we can also get some underlying probabilities, and it will give a little bit different shape to the function. So instead of trying to explain it at first, let me just show you first, and then we'll talk about it. So this is the same block of code, the same cell, except for now, instead of using the .predict method, we're using .predict proba for predict probability for these inputs. And now we see this sort of S-shaped curve. It is a sigmoid function. You can say it's taking that linear regression, what we looked at here, and it is squishifying it, to use the rigorous technical term, right? So we're taking that linear regression and we're squishifying it so that it stays between 0 and 1 here. And this is actually how the logistic regression is working, is it's producing this sigmoid curve. And then if you use the predict method, what it's simply doing is it's saying, okay, if the predicted probability is below 0.5, then we're going to say that prediction is a 0. If it's above 0.5, we're going to say that it's a 1. Because there may always be some uncertainty. These things are probabilistic, but if you're going to make a business decision, ultimately you have to say yes or no. Am I going to filter that email message if I think that it's spam, or am I going to take action on that insurance claim if I think that there's some risk of fraud? And so it's using that threshold of 0.5 predicted probability to say we're going to either round that down to a 0 or round it up to a 1. So that is a little bit about logistic regression. Again, a model for classification that is related to but distinct from the linear regression that we were talking about last night and then the night before. Now we're going to apply logistic regression and some other classification models to the Titanic data set to predict survival on the Titanic. But before I hop into that, let's just look at Slack again to see if there are any additional questions. Quinn, I see you asked, could we go over the generate data code? If you are interested in that, that is a function that comes from scikit-learn that you can just make fake data. And so if you Google scikit-learn make classification, you will see the documentation on that. I don't know if I ever used it before preparing this lesson. So in no time at all, you can know as much about it as I do. But it can be helpful for generating sort of these teaching tools where you want these simple data sets to demonstrate fitting a model to. Any other questions before we move on to the Titanic model? Okay, so we're going to predict survival on the Titanic. This is an example, this data set, I both love it and kind of don't love it. The nice thing about it is that a couple things. One, that it's sort of like the junior high science fair sort of experience where you kind of know what the answers are going to be up front, right? Or you can have a reasonable hypothesis. And so then that tells you if you're on the right track or not, and you can see some intuitive results as opposed to working with a more real world data set that you have no clue what sort of relationships you'd expect to see in the data set. So that's a nice thing about it. Another nice thing about it is it just seems to be a common example in the machine learning world as a way to get started with classification problems in machine learning. And in fact, there is a platform called Kaggle for practicing your supervised machine learning skills by doing different challenges or competitions. And this is one of their sort of getting started competitions. And so that's a fun way to get some hands-on experience, learn by doing. And for that reason, we've used this data set earlier in the course as well. So I acknowledge this is not the sort of thing that an employer is going to pay you to analyze or predict survival on the Titanic. But these exact same skills and these exact same Python libraries, you can apply them to all sorts of real-world examples like the ones we've alluded to earlier in the conversation. So first I'm going to load in this data. And I've split it into training and testing, because even in sort of contrived examples like for an intro lesson, I still want to always follow some best practices of splitting data into training and testing data. I never want to skip that step. So in our training data set, we have almost 700 rows or examples. And then in the testing data set, we have over 200 rows or examples, and each of them has 15 columns. We can take a look at the first 5 rows of the training data set, and here's what we see. This first column is what we will be using as the target, whether or not the passenger survived, whereas 0 means that sadly they did not, and 1 means that happily they did survive that disaster, the sinking of the Titanic. And we can use the pandas function value counts to see what percentage of passengers survived. And if we pass in this normalize equals true, it does show it as a percentage rather than as a count. And so we see that sadly the majority, over 60%, did not survive the passengers in this training portion of the data set. And so one thing we could do before we get into all sorts of fancy model types and how we pre-process the data, we could just think about, well, what would happen if we did the simplest thing there is and just predict that everyone did not survive. That sort of simple notion actually has a name. It's called the majority classifier. So simply predicting whatever the majority class is, you always use that for your prediction. And this might seem silly, but a pretty good book called Data Science for Business recommends that you not necessarily even skip this step. Yeah, it may seem like advice so obvious it can be passed over quickly, but there are cases where smart people have been tripped up in not thinking through this comparison. For example, say you make a classification model that gets 94% accuracy, but yet what if the majority class was 94%? Then you're not really adding any value with your fancy model necessarily, or at least you maybe need to measure that value in a different way with a different metric. And you might say, is it really that real world that it could be so imbalanced? Well, actually, in some of the use cases that we've talked about, it could be more imbalanced than that. In a fraud detection example, where you would have, maybe 99% of cases are not fraudulent and 1% are, or even 99.99%. Percent are not fraudulent. So accuracy may not be the best metric. And if you're working at your first data science job and some vendor comes to your boss's boss and tries to sell them some sort of product to say we're going to detect the fraud in your business with 99% accuracy, you may want to ask some questions about what that really means, because you could get that just by simply predicting that every case is not fraudulent. But that wouldn't be useful. The point of having a fraud predictor is you've got to make some positive predictions, right? So I don't want to belabor the point too much. So let me move on and just show you how this plays out in the Titanic example. This will just help to confirm your intuitions. You may have a guess of what the accuracy would look like. But I can generate predictions to just say, give me a list. If I multiply a list by a number, then it's going to give me that list repeated that many times. So I'm having a list of zeros that's the same length as the training data set. And now if I use this accuracy score function, I can see that, okay, well, that majority classifier would get 61.4% accuracy, which matches this base rate of the majority class. The accuracy score is, if we could calculate this by hand. I'll show you in a moment how it is calculated. But we can also import this from the scikit-learn library. It's the most intuitive error metric for classification, but it may not always be the best, or it might not properly capture the various trade-offs that you might need to think about when making business decisions. So there's also this function called a confusion matrix. And here's what this looks like. The core of it here is just this, and then I'm putting it into a pandas data frame with some labels, so that it's not just 4 numbers, but that you have these labels to show what it means. And so the confusion matrix may be confusing to you at first. It certainly was for me the first times I looked at it. So don't worry or be discouraged. But each cell, this is showing right here the true negative predictions. So where the person truly did not survive, and we predicted that they wouldn't survive. Here are the false negative predictions. So we predicted that they would not survive, but they actually did. And then here in this column are the ones that we predicted that they would survive. And those can be true positives or false positives. Well, we never, in this sort of naive baseline, we never predicted that someone survived. So we just have zeros in this column. And so that model is not going to be useful to us if we were trying to actually predict something happening. So there's another metric called recall score, and recall here would show us why the majority classifier is not useful to us in this case. If we always predicted that they would not survive, in other words, we never predicted that they would survive, then we're going to have 0% recall. The idea of recall here is we can calculate it this way by saying, okay, how many times did the positive class occur, in this case survival, the thing you're trying to predict, how many times did that thing that you're trying to predict, how many times did it occur? That's in the denominator. And then the numerator is how many times did you actually detect what you were trying to detect? And in our case, that was 0. So we, even though we had this 60% accuracy, we had no recall. And accuracy, not to over-explain it here, but that's simply taking, okay, well, what were our correct predictions, and then dividing that by the total number of predictions. So let me pause here for questions before we dive into making a real model. Great question about Bayes' theorem. I like Aaron's answer. Absolutely, that would be something that we would go into more in the full course. I'm going to keep on moving. So the The next thing that we're going to do in making a full model, we want to actually use some of the features that are in our data set. So we might want to test this hypothesis of women and children first when there may be a limited number of lifeboats and we're in a survival situation. And so I'll take a look here get some info from pandas about these two columns in the data set. And I see some issues with both that are going to have to be addressed before we use them in a scikit-learn machine learning model. So the issue with the gender or sex column is that it is not a number, it's an object. As we saw here, if I scroll back up to the table, here it's encoded as a string, as a word, either male or female. Our model is going to expect that to be encoded as in a format that it can deal with, and not just a string. Age is represented as a number, so that's a good thing. However, there are some missing values here, and I know that if you remember back to last week when we were learning about pandas and worked with the Titanic data set with Ryan A., then you dealt with missing values. So this will be a little bit of a refresher or a review. We see here in the age column, there are 535 non-null values, but yet 668 total entries. So we're going to have to deal with that in some way. And so first we'll go ahead and we'll encode the sex column. And there's a variety of ways that we could do this. There are so many different ways. One way that we could do it is with this block of code here. And let me run the one below it as well to see what we've done. So I can actually create a new feature or a new column in the data set, and I'm going to call that female. And the way that I'll do that is I'll say, okay, look at the sex column and say, does it equal female? True or false? And those true or false values will be put into a column here. As you can see, if I put those two columns side by side and I look at the head, the first 5 values, you see that they correspond to this column is true when this column is female. This column is false when this column is male. So it has the expected behavior. And you might be thinking, well, this doesn't look like a number to me. Well, to the computer, a Boolean value does look like a number. It's the same as a 0 or 1. So this is actually okay. But if for aesthetic reasons or whatever reasons we wanted it to really be a number, we could make that conversion explicit if we'd like, and if we do it this way, now we're going to get the zeros and the ones. You'll also note that we had to do this both in the training data set and in the testing data set as well. We need to encode both and to have a consistent encoding between the two. So that's how we've encoded sex now as a number that the machine learning model can deal with. Now we're going to have to deal with those missing values for age. And we actually have 2 options here. We could either drop rows from the training data set where age is missing, or we could impute a value, which is just a fancy word, if you recall from last week, for filling in the missing values so that they're not missing anymore. In the training data set, when we're working with training data, then we can throw out whatever rows or columns we want to. For outliers, for missing data, for whatever reason, we can do what we want in the training data set, but in the testing data set, we cannot throw out any rows. So if we expect our algorithm to work if there could be missing data in the wild, if we, for example, we're using a more real world example, with fraud detection or spam detection. If you would expect that in production, in the real world, when you're using this product or this algorithm, if it's got to work with missing data, then you can't throw it out when you're testing it either. But when you're training it, you could. In any case, we'll go ahead and impute it here. We won't throw it out. So we see here, this is the pandas function that will tell us how many missing values we had in the training set. Then we'll take a look at what the average age is for the training set, because that would make sense as a value that we could fill it in with. It's not the only option. We could fill it in with the median. We could fill it in with some sort of special code like -1. There is a variety of options for imputation. We could even try to come up with some sort of a model that would try to guess their age based on the other columns. But for here, we'll do the simpler thing. We will fill in the NAs, or the not a number. We'll fill it in place with the mean age, which we see is 29.9 in the training data set. So if we run that, then we see that now there are no more missing values because we filled them in. And in the test set, we also have some missing values for age. We see that there are 44 of them in the test set. And the average age in the test set is basically the same, slightly different. Instead of 29.9, it's 29.1. The best practice would be to fill in the test missing values with the mean age from the training data set. Because if you were to use the average age from the test data set, which could differ, it might help your performance in an unrealistic way that may not generalize to the real world. I don't have the time to get into a lot of depth on this point, but this is just a little practical bit of applied machine learning practice that in this case is honestly not going to really make much of a difference here, but is just a best practice to think of and be aware of. So in any case, we filled in the missing ages from the test data set with the average age from the trained data set, and now we have no more missing values. So now we can go ahead and do a logistic regression model to predict survival as our target based on two features of the gender, whether or not the person is female, and the age. And so we're saying that's our features, that's our target, and we are going to use a logistic regression model like we looked at earlier tonight with the squishified sigmoid curve. And we're going to fit that model and then report on the training accuracy and the test accuracy like we did last night with our train and test error for the linear regression models. So let's take a look here. So we fit that model, and we have some improved accuracy compared to the majority classifier, that naive baseline of just always predicting that someone did not survive. So our overall accuracy improved. It's very similar from train to test. They're at about 78, 79%. We can look at a confusion matrix as well and see that now we don't have any zeros here. We have the full range of possibilities to where we have some true positives in this cell right here. We have some true negatives in this cell right here. We also have some false positives right here highlighted and some false negatives right here. So now our recall score is not going to be a 0. Now we have recalled or found 70% of the people who survived. This thing we're trying to predict, survival, we've correctly found 70% of those cases. we can see the way that it's calculated here. You take the survivals that we predict, the survivals that we correctly predicted, which are 59 true positives, and then we divide that by the total number of positives. So the people that survived that we did predict, and the people that actually survived that we missed, that we didn't predict. That sum is in the denominator, and if we calculate like that, we get this exact same number here. That's the recall score. There are a variety of other metrics, many of them, in fact, that can be derived from different combinations of this confusion matrix. And then the accuracy, again, we're taking this diagonal in this matrix are the predictions we got right, and then we add up all 4 of them together, and that's the total number of predictions. So the ones we got right divided by the total number of predictions, and that's that accuracy there at about 78% test accuracy. I'll pause here for questions again, because we've covered a lot of ground. Let me check Slack. So yes, great question. I'm not sure if you asked that right before I addressed it, but yes, there are a variety of things that you can do with filling in missing value, including the median. Absolutely. Any other questions? The indices, that is just referring to the rows, that these came from in the original data set, and when we broke this up into train and test, the split was random, and so that's the reason why we have the indices are non-consecutive, and they're not even and they're non-monotonic. So an overly fancy word to say that they're not even always going up or going down. Because that's not a bug. That's a feature. It's showing that shuffling action of the train test split is working as desired. But those can be safely ignored. I apologize for confusion there. Saw this a few times. Why do you manipulate or convert the data after you break into train and test sets and not before? That's a great question. I'm really glad that you asked it, because it certainly would be more convenient, something like this, to do it beforehand, before breaking them up. And there are certain things that you safely could do before splitting them. But the best practices would be to look at the test data as little as possible. You potentially can even do a more than just a train test split. You can do training data and then cross-validation with your training data. And I apologize for introducing that vocab term, because I'm not going to have time to explain it right now. We would in the full course. Or you could even do a 3-way split where you have train, validation, and test. And in that case, the terminology may differ on what people call a test set versus a validation set versus a holdout set. But there's this idea that really, if you want to get an idea of how well this is going to generalize to truly unseen data, future data, then the idea would be to have some sort of data set that you truly hold out and you don't touch until the very end, after you've made all your decisions of what sort of model you're going to use with what sort of parameters, what features you include, how you pre-process them, what new features you engineer. You make all those decisions first, and then finally you have this moment of truth where you unlock the test set from the vault, you take it out, and you say, how does it do on the test set? And then you're going to have to pre-process that test set in a matching way. But the ideal would be that, oh, hey, you've followed this great hygiene if you didn't touch it or look at it until the very end. So this is simulating that a little bit. I don't know if it's overkill for the purpose of this intro lesson. Maybe I shouldn't have made that choice. So I hope that helps and didn't muddle things more. But that's the logic there. But it's not that one way is completely right and one way is completely wrong. Yes, you are doing the same for some of the procedures. You're doing the same thing, like saying, okay, I'm going to engineer this feature, this column that's called female. You're doing the exact same thing on both. So that would be the sort of thing that, yes, you could do that up front. Other things you're doing it differently because you're potentially encoding a categorical variable using the categories that are seen in the training data set, and you're applying the training categories to the test data set. So if you did that before splitting, then that would actually not work as well for you. You could potentially run into some issues where then when you go to productionize it, the model doesn't perform as well as you expect, or you run into some bugs that you didn't expect. So encoding categorical variables would be something where you do that after train and test if you want to really simulate the challenges of the real world. Imputing missing values would be something where yes, you impute missing values in the test set based on what you see in the training set, not in the test set. So some things are the same, some things are different. So I'm going to go ahead and come back here to our logistic regression model, where again we use just the two features, the gender and the age, and we'll take a look at, like we did last night, we can get some coefficients from this model and an intercept, because even though it doesn't look like a line because the line has been squishified with what's called the sigmoid function, it still has a linear combination of coefficients like a linear regression model. So if this output is a little bit cryptic, we can put it, we can display it in a slightly different way with a plot here, where we're seeing, okay, here's now the logistic regression coefficients. This first one is the coefficient for whether or not the passenger is female. And the second one here is a coefficient for the passenger's age. So it makes sense, first of all, the sign for both of these coefficients. That this corresponds with our hypothesis that if the old adage, women and children first, if that's true, then we would expect being female to be associated with a higher probability of survival, and the coefficient being positive matches our intuition or hypothesis there. We also, if the idea of children first, that means that age we would expect to have a negative coefficient, and it does. Now, the fact that it's much smaller compared to female doesn't necessarily mean that it's so much less important than gender. Part of what we have going on here is some different units. Female is ranges either 0 or 1. And that's what that's getting multiplied by. But age has a much wider range, right? From, in this data set, I believe it goes from 0 to 80. And so this is the coefficient that is associated with each year of the age. So with each increasing year, of age, you multiply it by this small negative number, and it's decreasing the probability. Also, the fact that the intercept is negative, that's intuitive as well if we stop to think about it, because the idea that the sort of the base case is that the passenger did not survive, and the gender can increase that, and then the year excuse me, the age can decrease it. So we see some fairly intuitive results there in the logistic regression. Now like we did last night, we'll look at a decision tree, but this time instead of a decision tree regressor, we will use a decision tree classifier. But otherwise, the same sort of concepts as we'll see in a moment. I'm going to check Slack here really quick. I'm going to come back to this question at the end. So for the decision tree, we are going to use what's essentially the same code. We are going to prune the tree from the start. We're not going to let it grow out of control. So there's some different parameters that can be used to prune the tree. This is a slightly different parameter than the one that we used last night. But you'll see in a moment as we visualize the tree what that does. But again, it's very similar code here, really just the first two lines that are differing, and we'll train this decision tree model on, again, the features of gender and age. And we end up getting extremely similar accuracy to the logistic regression. So it didn't do better. It didn't really do worse. I mean, the training accuracy was slightly better. The test accuracy, which is more important, is slightly worse. But really, it's basically the same quality model. Again, the recall is not 0 anymore. The recall here, this model found 3/4 of the survivors that we're trying to predict. So here's this confusion matrix. And a decision tree does not have coefficients, but what it has is something called feature importances. And these numbers are always going to be positive, because I would say this is both a bug and a feature. It's just a trade-off with the decision tree model. So the good thing about the decision tree is that it can capture nonlinear relationships. So maybe you have something that doesn't increase at a straight line, maybe it increases exponentially. A decision tree can fit that nonlinear relationship better than a linear model can. A decision tree can even capture non-monotonic relationships, to use that sort of fancy vocab word, where you maybe have something that's like a sine wave, where it goes up and down. So decision tree and models that are based on trees can capture those. And you might wonder, when does that happen in the real world? Well, you can think about, to use an auto insurance example again, as you might expect, in general, drivers that are younger, that have turned 16 or gotten their driver's license for the first time, are a higher risk. And then as the driver gets older, then they become a lower risk of having auto accidents. But then later in life, then the risk starts to come up again as drivers get older, and their reaction times may slow, their vision may decrease. And so that's an example of a relationship that is nonlinear and even non-monotonic. It goes down and then it goes back up, age versus driving risk. So it's a great thing that a decision tree can capture those relationships, but because of that, it's not going to give you coefficients like you get in the logistic regression that have a sign associated with them that says, okay, when this thing increases, then the target decreases, or to have a positive or negative associations. So in the decision tree feature importances, those will always be positive values, and it has to do with how often this variable is used in the splits for the tree. But this is a very shallow, simple tree, so we shouldn't overanalyze this information here. There's some care that needs to be applied in the analyzing of the feature importances. But just wanted to present that in these models, even these nonlinear models, they're not complete black boxes. That's the key takeaway here, that there are ways to try to peek into the black box, and we'll teach you more about that in the full course. Kind of coming to the end here, let's visualize this tree again, like we did last night. It does require this GraphViz library, which I've already installed. And if I visualize this decision tree, it looks like what we would expect it to look like for the women and children first hypothesis. So the decision tree tries to find what's the best feature to branch on to sort my data into two groups that have differing probabilities of survival. And so it finds that, okay, yeah, not that there was a lot of options here for the decision tree to choose from. It'd have to either choose female or age. Those were the only two features. Although for age, since there were a lot of different values for age, there'll be a lot of possibilities on where you could split for age. And the decision tree tries a variety of possible split points and tries to find the best one. But in this case, this gender of whether or not female, this was the best split point at the beginning of the tree. And so in the base case is that the passenger did not survive, and we apply this rule here that the decision tree has found female is less than 0.5, which is just a funny way of saying if true, then this is the not female, this is the male path. And now we have some increased confidence with this darker shade of orange here that the passenger did not survive. But we are going to do another branch here and say, okay, well, what if we've got males here? When we're right here, we're dealing with males. But what if these males are age 14 or less? If they're age 14 or less, then even though they're male, then we're going to predict that they survive. So these are the male children right here. So male children, and there are not a ton of them in this data set. We have 30 here. But for the 30 male children, age 14 and under, we're going to predict that they survived. Not because all of them did, but out of the 30, 17 did, 13 did not. So we had more survivors, and that's what we're going to predict for the male children, that they survived. But for all of the males who are not 14 or under, we're going to predict that their class is that they did not survive. Again, we know in the training data that that's not always the case, but the strong majority of the time, 340 out of 407 adult males did not survive. So that's what we're going to predict. Going down this branch, if the passenger is female, then we predict that they survived. And we're still trying to the decision tree. You might wonder, why does it split again? If we already had, it's kind of funny, like, okay, this one is survived, and then it splits into survived and survived. But you may not be able to see it in the screen sharing, but these are different shades of blue, which is color coded. So essentially it's saying if it's a younger female, although in this case, using a different age threshold of a female in their early 30s or younger, then we're extra confident that they survived. Because 57 out of 68 of the younger females did. If they're older than that threshold, then we're less confident that they survive. So we could get, again, the underlying probabilities may be different, even if ultimately that binary class remains the same here. So In this simple decision tree, we have created a baseline model that explores that sort of intuitive hypothesis. And this would be a great branching off point to say, what other features could we try? What other model parameters could we try to improve the accuracy of predicting survival on the Titanic even further? And that's what we'll do in this assignment here in just a minute. I have no more code in this notebook, but just want to share some thoughts on why I presented starting with some of these simple models. And this was actually some advice that I had received from a mentor. So now I'm passing it along to you. So I haven't really explained my background here, but I recently joined Lambda School after a dozen years in the insurance industry, just because I believe in the mission of Lambda so much. I'm so excited about it. But before that, as I said, I worked in insurance companies, including my hometown in the Midwest happens to be the national headquarters for two different insurance companies, one of which you've certainly heard of, State Farm Insurance, Fortune 50 company, the largest insurer of homes and automobiles in the country. If you had a bad experience with State Farm, don't ask me about it. I don't work there anymore, and I worked on different things. So I was very privileged to be able to begin my data science career officially there. I was a career changer, just like many of you might be contemplating a career change. I was working as sort of like a business generalist bureaucrat, which, as you can imagine, there are many of those, maybe too many, in the cubicles of the insurance companies. And I said, you know what? I don't really know if this is the life I want, because I feel like I'm a sharp guy and I could do more. I could have more intellectually interesting work, and I could also maybe better support my growing family if I started to learn more about this thing I've started to hear about back in 2012 called data science. Sounds like a lot of fun, and I also see that those skills are rare and valuable in the marketplace. Employers just can't find enough of people with these skills. So I would like to learn this. One problem: I'm in the middle of the Midwest. There's no university nearby. Well, at least not in my town without a commute where I could learn this from. And even if I did go for a traditional master's degree or second bachelor's degree, you know what? That's going to take a lot of time. That's going to take some money, and that could be risky. That student loan debt. So instead of letting that stop me from changing careers, instead I relied on mentors. I relied on information online. Lambda School didn't exist then, but I still use the information online, which can be overwhelming to sift through and took me longer. This career change took me years instead of a period of 30 weeks. But I was fortunate to find a mentor who shared with me this advice about the baseline models. And he said, your first goal should always, always, always be to get a generalized prediction as fast as possible. Some sort of simple model like a logistic regression or a shallow decision tree that gives you a sanity check on, can I beat an even simpler baseline like the majority classifier, like predicting that all passengers on the Titanic perished, or that all claims are not fraudulent, or all emails are not spam. That by doing that, you're going to set a benchmark for yourself, and then you're going to also see, well, how much more effort should I put in to try to work with some additional features and process those features in some different ways, or create some new features, do more feature engineering, try different model types, try different parameters of the model. Well, if your initial efforts are good enough, then you might want to stop there. Maybe that's good enough for the business. And if it's not good enough, then by starting with a simple baseline and then iterating and trying small changes and seeing what happens, then you'll know what a difference your efforts make. Whereas if you tried to make your best model from the very beginning, then you're not going to know, well, what part of my efforts really made the most difference? You're not going to know if you didn't do it iteratively. So I like to end my lessons with links to more reading information. And here are some additional articles that echo and elaborate on my mentor's advice. If you're curious in learning more about this practical philosophy of applying machine learning by beginning with baseline models. So we are out of time. I will take a look at Slack in just a moment, but I also want to share your assignment with you. There is just one question, which I will drop into Slack here. So this assignment is to work with the Titanic data, to load that in using this cell, and then to train a logistic regression, a decision tree, or even a random forest, which we have not taught yet, but you could read about that. You could try that if you're feeling adventurous. So try one of those three models from scikit-learn. Use any features you want to, any parameters you want, and see if you can get better than 78.0% accuracy on the test set. As I said here, that's not a strict requirement to finish this assignment, but that would be encouraged as a goal to try. And if you do this, then you might be ready to tackle something like a challenge on Kaggle, that platform I mentioned before. That you could work with the Titanic data. Their version of the Titanic data is a little bit different than the version that we're using here, but the same tools and techniques would still apply. So that is the assignment. I'm excited for you to tackle this final assignment of the intro course. And again, so privileged that you would choose to spend your Friday evening and these past 2 weeks with us. And I certainly hope that you'll be spending more time with us if you apply to be a member of our next data science cohort with Lambda School. So thank you.
Great, thank you. And I will just echo all of that and just add that although this has already been said, but just to be completely clear, you've had 8 lectures with 8 assignments, and those assignments are essentially the pre-course work. Hopefully you've also submitted 7 and soon to be 8 stand-up forms. If you haven't, you should, because that's how we know you actually did it and you shared it with us and we can see it. Now, that said, you don't have to have them all finished. You have until November 1st to get them all finished. And I will even acknowledge that, we put a lot of stretch goals. We put a lot of like, oh, it'd be cool if you try this thing. We are not expecting every notebook to be perfect and complete through all the stretch goals. If you're able to do that for any notebook, that's great. But really what we want to see is that you engaged with this material, you perhaps struggled with it a bit, you got through it, and you were able to get some results and show some promise to learn more, because that's what this is about. So any questions about that, of course, ask. And even though this course is done, you can still use this Slack community to chat about the assignments ahead of them being due and to ask questions. We probably won't respond quite as promptly as we have been right now, but we'll still try to check in every day or so. So any questions? We all ready to start the last assignment? Great. All right. Well, thank you, everybody, and I'll have the video up shortly.